In the world of industrial visual inspection, the choice between YOLO and OpenCV isn't just a technical preference, it's a strategic decision. It determines the speed, accuracy, and cost of your inspection systems, affects the integration with PLCs and SCADA, and ultimately decides whether your AI deployment runs in milliseconds or in minutes. Manufacturing inspection systems face conditions that are far from ideal: variable lighting, moving conveyors, vibrations, dust, reflections, and real-time constraints. Here, every millisecond counts. If a label is misaligned, a package is dented, or a component is missing, the system must detect it instantly and signal the PLC to take corrective action before the product exits the inspection bay. Both YOLO and OpenCV are powerful, but they belong to different layers of the computer vision stack. Understanding how and when to use them, or both together, can mean the difference between an efficient smart factory and a bottleneck prototype. The core difference: traditional vision versus deep learning. Before diving into their technical comparison, it's crucial to understand the philosophical difference. OpenCV, open source computer vision library, is a traditional image processing framework. It doesn't learn in the deep learning sense. Instead, it provides low-level tools for image manipulation, feature extraction, edge detection, morphological transformations, and more. It's the backbone of many classical vision systems used long before AI became mainstream. YOLO, you only look once, on the other hand, is a deep learning-based object detection framework. It uses convolutional neural networks, CNNs, to identify and localize multiple objects in a single image, in real time. In manufacturing, OpenCV is ideal for rule-based, deterministic inspections. Detect if this label is centered within 3 mm tolerance. YOLO is ideal for contextual or complex detections. Detect if a part is missing or wrongly assembled. Let's explore these layers technically. OpenCV, the classical powerhouse. OpenCV is like a Swiss Army knife of image processing. It's C++ under the hood but has Python bindings that make prototyping lightning fast. In manufacturing inspection, OpenCV shines when the inspection logic is well-defined, environmentally stable, and computationally constrained. How OpenCV works technically. OpenCV operations typically follow a deterministic pipeline. 1. Acquire image from camera. 2. Preprocess image, grayscale, blur, threshold, etc. 3. Detect features or contours. 4. Apply geometric or pixel-level logic. 5. Decision, pass, fail. 6. Trigger PLC signal. How OpenCV works technically. OpenCV operations typically follow a deterministic pipeline. Advantages: lightning fast on CPU, 10-100 FPS easily achievable, zero need for GPU, highly interpretable, rule-driven logic. Easy PLC integration, via I/O triggers or fast API endpoints. Limitations: fails under lighting variations or shape deformations, needs extensive tuning and parameter calibration, cannot generalize to unseen defects or variations. OpenCV works beautifully for binary or shape-based inspections, verifying label presence, detecting orientation, measuring distances, or ensuring surface cleanliness through thresholding. YOLO, the deep learning disruptor. YOLO is a single-shot object detector. It predicts bounding boxes and class probabilities simultaneously. That's where the name comes from. The network looks at the image only once to make predictions, as opposed to older models like RCNN that required multiple passes. How YOLO works technically. YOLO divides an image into a grid, say 13 × 13. Each grid cell predicts bounding boxes, X, Y, W, H, confidence scores. Class probabilities. For industrial inspection, YOLO 8 can detect multiple object classes, e.g., label, cap missing, seal defect, handle diverse lighting and orientation conditions. Run on GPU, CPU, or edge devices like NVIDIA Jetson or Intel Movidius. Here's a minimal inference example using Ultralytics YOLO 8. Advantages: learns from examples, no need to manually define rules. Robust to lighting, angle, and noise variations. Detects multiple defect types simultaneously. Easy retraining for new product lines. Limitations: requires labeled data and model training. Higher inference latency, 10 to 60 milliseconds per frame on GPU. Needs GPU or optimized edge accelerators for high throughput. In a production environment, YOLO models can be deployed via FastAPI as REST APIs, connected to a PLC through OPC or MQTT, sending a pass or fail signal based on detection confidence thresholds. When to use which? The decision matrix. Let's map this into an industrial decision framework. Rule of thumb: use OpenCV for tightly controlled, high-speed binary inspection tasks. Use YOLO for dynamic, multi-object, or variant-driven inspections. Combine both for hybrid inspection systems, OpenCV for preprocessing, YOLO for decision-making. The hybrid approach: best of both worlds. In practice, Avizops and many advanced industrial integrators use YOLO plus OpenCV together. Here's an example. A packaging line needs to ensure that a label is not only present but also perfectly aligned and printed. YOLO detects the label presence and region, while OpenCV analyzes that detected region for alignment and print quality. This hybrid design often outperforms pure deep learning or pure traditional setups. YOLO takes care of variability and generalization, while OpenCV ensures deterministic precision. Edge deployment and optimization: for deployment on factory floors, inference latency is king. A typical configuration might look like: camera, basilar, FLIR industrial camera, Gigi Vision, hardware, NVIDIA Jetson Xavier NX, Intel i7 plus RTX 3060. Framework: YOLO 8 plus OpenCV plus FastAPI. Integration: MQTT to PLC or SCADA. To achieve maximum FPS, convert YOLO model to ONNX or TensorRT engine. Use CV2. CUDA, functions for preprocessing, GPU accelerated OpenCV, batch inference multiple frames. Use async queues between capture and inference threads. A highly optimized YOLO 8 tiny model can achieve 60 FPS on Jetson Xavier NX, whereas a hybrid OpenCV YOLO pipeline often delivers 90% detection accuracy with real-time feedback loops to PLCs. Real-world example: label validation system. At one of Avizops' FMCG client sites, a packaging line needed to ensure that 1. Each product has a batch label. 2. The label text matches the production code from ERP. 3. Labels are not tilted beyond 5 degrees. The final system: YOLO 8 trained on 8,000 label images for presence and position. Easy OCR integrated with OpenCV for text extraction. Alignment validated using OpenCV's Huff transform. FastAPI API layer communicated results to PLC via MQTT. The results: accuracy, 97.8% label validation rate, throughput, 40 FPS on edge Jetson integration, MQTT feedback loop to stop conveyor instantly upon mismatch. This kind of system blends the intelligence of YOLO with the precision of OpenCV, forming a production-grade inspection ecosystem. Complement, don't compete. The YOLO versus OpenCV debate shouldn't be seen as a rivalry. They're complementary technologies addressing different problem depths in the same vision pipeline. OpenCV gives you control, pixel level, rule-driven, and deterministic. YOLO gives you understanding, contextual, adaptive, and learning-based. Sample system architecture. In the end, real-time industrial inspection isn't about choosing one over the other, but about engineering the right blend of both, ensuring every decision, every millisecond, and every frame contributes to a smarter, faster, and more reliable factory floor.